Welcome back to more of the Chapter 9 practice test for Calculus BC. And in these next set of problems, numbers 12, 13, and 14, we're going to be taking a look at some improper integrals. So my attitude for all of these improper integrals is we should find the antiderivative first. So that's what we're going to do. We're going to find the antiderivative to a few of these integrals to start with. So firstly, let's take a look at number 12, and let's find the antiderivative of 2 over x squared minus 2x. Now my first thought for these is never, can I try an advanced technique? I always try to look at these and say, is there a simplification that I can do here to make this easier? And of course, there really isn't. Next, I'm going to say, is there a u substitution I can make? Because a u substitution is a not very invasive technique. And, if you make u equal to x squared minus 2x, there's nothing going to be in this antiderivative to balance that out. So I am stuck looking at some more advanced technique. And it just happens in this case that the technique that's going to be best suited is going to be a partial fraction decomposition. So I'll set up my partial fraction decomposition and do some algebra to figure out how the numerators have to behave to make this equation true. Next, we'll substitute some convenient values for x, starting with x equals 0, which tells me that 2 is equal to a times negative 2, which is a equals 1. The next convenient value here is x equals 2, which makes my equation 2 equals 2b, or b equals 1. Putting that aside, we now have a simplification for this antiderivative. This is going to be the antiderivative of negative 1 over x plus 1 over x minus 2 dx. Now, if you're uncomfortable with natural log integration, then I recommend you make the u substitutions necessary here. However, there really isn't a whole lot to worry about with this one in particular, because when u equals x, and this antiderivative is just the natural log of x, and if u equals x minus 2, then du is equal to dx. There's a pretty clean substitution there. So this antiderivative is just the natural log of x minus 2 plus constant. And that simplifies to the natural log of x minus 2 over x plus constant. Now that I have my antiderivative, I can start looking at the definite integral. So we're going to look at the definite integral from negative infinity to 2 of 2 over x squared minus 2x dx. We'll replace that infinite lower limit with an a and do a limit as a approaches negative infinity instead. And now that I've found my antiderivative, I can make this substitution really easily. This is equal to the limit of the natural log of x minus 2 over x from 2 to a. Using our substitution, we'll get the natural log of negative 2 minus 2 over 2, in absolute values, of course, minus the limit as a approaches negative infinity of a minus 2 over a. Now that first term is just the natural log of 2, but that second term, we're going to have to do a little bit more advanced technique in order to figure out this limit. So since we're going to negative infinity, I'm going to divide everything by 1 over a. That's going to have the effect of transforming this limit into 1 minus 2 over a over 1. Now as a goes to negative infinity, it doesn't really matter that whether this goes to positive or negative infinity. This 2 over a is going to approach 0. So I'm left with the natural log of 1. I just realized I was running out of real estate on the screen. So this is what we should be looking at. Let me space this out just a little bit for you. There we go. We've got the natural log of 1 minus 2 over a over 1. And this is 2 over a is going to approach 0, which means this just becomes the natural log of 1. And of course, the natural log of 1 is 0. So this is equal to just to the natural log of 2. All right, a little bit of integral review. That's okay, never hurt anyone. We were ready for number 13 now. And now we have the integral from negative infinity to 0 of x e to the 2x. Again, I'm going to take the approach of antiderivatives first. And looking at this antiderivative, my first thought is to try a u substitution. And if u is equal to 2x over here on the power, then of course du is just going to be equal to 2. And then there's nothing to balance out the x that I just highlighted. So u substitution is not going to work here. And apparently the next thing we're going to have to try is an integral by parts. So this looks like a pretty good candidate to use a tabular method for integral by parts. So tabular method will set up a u and a dv into two columns, x and e to the 2x. Take the derivative, 1. Take the antiderivative, 1/2 e to the 2x. Take another derivative, because I see we're going to get to 0. And then another antiderivative, e to the 1/4 e to the 2x now. And then we'll just assemble that. So that's going to be equal to 1/2 x e to the 2x minus 1/4 e to the 2x. Now we can probably simplify that. In fact, we definitely can simplify this. And we'll factor out 1/4 and we'll factor out an e to the 2x. And that should give me 2x minus 1 plus constant. So this antiderivative is pretty cheaply had. Not a big deal. Hopefully, if you've been studying with your integral by parts, this is an easier one. So now we'll start with the definite integral from negative infinity to 0. And we'll make this a limit and make the lower limit go to negative infinity. Now we use our antiderivative strategically. So we're going to make the limit as a approaches negative infinity of our antiderivative, evaluated from a to 0. Substitute and subtract. Let's work on this first half here. E to the 0, of course, is just 1. 2 times 0 minus 1 is negative 1. So that first term is negative 1. And now for the limit, as a approaches negative infinity, 1/4 e to the 2a, well, the 1/4 is constant, so we'll just write that there. But e to the 2a, as a approaches infinity, 2a approaches negative infinity, and e to the negative infinity approaches 1. Basically, the negative exponent here means that we're actually looking at 1 over 2 to b, as this b goes to positive infinity. And of course, since the denominator is growing without bound, this is going to go to, well, it's going to go to 0. So this is 0. And then as a approaches negative infinity, 2a minus 1, let's do this over here, the limit as a approaches negative infinity of 2a minus 1, well, that's going to approach, well, yeah, that's going to approach negative infinity. This keeps on getting smaller and smaller without bound. So what we're looking at is an indeterminate form. We're looking at a 0 multiplied by infinity. So now that we know it's an indeterminate form, we're going to set up to use L'Hopital's rule by trying to turn this into some kind of a ratio. So the easiest way to do that, I think, is to, instead of e to the 2a, we'll put e to the negative 2a in the denominator, and we'll keep 2a minus 1 in the numerator. and we'll use L'Hopital's rule. The derivative of 2a minus 1 is just 2. And the derivative of e to the negative 2a is negative 2 e to the negative 2a. That's going to simplify to 1/4 the limit as a approaches negative infinity of e to the positive 2a. And as we already discussed, this is going to go to 0. So when you put it all together, you get that the integral from negative infinity to 0 of x e to the 2x dx, that's just negative 1/4. Finally, we have the integral from 0 to natural log of 2 of e to the 1 over x squared. Like our previous problem, I'm going to look at this as the antiderivative first. Now I'm going to re-express this as 1 over x squared multiplied by e to the 1 over x. And the reason why I want to do that is because I noticed that the derivative of 1 over x is negative 1 over x squared. So the derivative of the power of e is already in the integrand, offset by negative, but still there. So for this integral, all I really need to do is a u substitution. So if I make my u 1 over x, negative du is going to be 1 over x squared dx. Making those substitutions, we get e to the u negative du, which the antiderivative of that is just negative e to the u plus constant, or negative e to the 1 over x plus constant. There's my antiderivative. Now I'm going to start with a definite integral. This definite integral has a problem at x equals 0. At x equals 0, we get some undefined stuff. So we're going to substitute that 0 for a limit as a approaches 0 from the right side of the integral. Since I have my antiderivative, just like the other ones, it's a lot easier just to put in the antiderivative now and use the substitution. Making my substitutions, I get negative 1 over natural log of 2, negative e to the 1 over natural log of 2, plus the limit as a approaches 0 from the right of 1 over a. Well, what happens to 1 over a as a approaches positive infinity? And if you said that this approaches positive infinity as well, you're correct. Well, what happens to e as its exponent goes to positive infinity? Well, this entire thing, therefore, also has to go to positive infinity because e is an exponential base, and that's greater than 1, so it's going to approach positive infinity. Now, if this second addend is approaching positive infinity, is this really going to matter? And the answer is no. So this is going to approach positive infinity. So the entire integral approaches positive infinity, which is to say that it diverges. And that does it for this video. We have looked at some pretty intense antiderivatives, so we'll see you on the next one. Have a good one.